Now we're going to look at actually graphing polynomials, just getting a quick sketch. We want to be able to look at a polynomial and be able to determine what's the general shape of this polynomial. What's it doing at the ends, what's happening at the x-intercepts, and what's going on. Where is that y-intercept at? So if we're graphing a polynomial, those are the things we need to know. Those are the things we want to be able to extrapolate from looking at the polynomial. So let's just look at some really basic polynomials. First off, let's look at our linear polynomial. Y equals ax plus b. Well, we know if we graphed that, it would just give us a straight line. Something like this. Could have a different slope or anything, but that's just kind of the general shape. Could be in a different location, different angle of rotation, but that is the general shape of a linear polynomial. Quadratic polynomial, its shape, we call that a parabola. And it's going to look something like that, just depending on what the a, b, and c happen to be, but that's the shape of it. Ax cubed plus bx squared plus cx plus d, that's our cubic polynomial. I don't know if any of you are familiar with what the cubic polynomial looks like, but its shape will be similar to that. And then the quartic polynomial, x to the fourth degree, it's going to have a curve along those lines. And then the coefficients are really what dictate where this is happening, what the overall stretches of each of these are. There's a couple of observations I want us to make about these general shapes of these polynomials. First one is the maximum number of terms that a polynomial can take. And that's just looking at how many times we change direction. Well, if you look at the linear function, how many times does the linear function change directions? None. It goes straight. If it starts increasing, it stays increasing. Okay? We'll look at the quadratic function, x squared. How many times does it change directions? Well, this one's coming down and it turns around one time. The x cubed, how many times can it change directions? Well, it's going up, then it's going down, then it's going back up. So we can see that it changed direction twice. And then the change of direction on the quartic we can see is once, twice, three times. So the number of changes in direction for this one was 0 times, 1 time, 2 times, and 3 times. So can we kind of come up with a conjecture, or can we make a conjecture about the relationship between the number of turns a polynomial can make and the actual degree of the polynomial? Well, if you'll notice, 1 to 0, 2 to 1, 3 to 2, 4 to 3, the maximum number of turns a polynomial can make is always 1 less than the degree. So the degree minus 1 will always give us the maximum turns of the polynomial. Next, I want to look at the end behaviors of these polynomials. And that's just looking at what they're doing, as they approach negative infinity and as they approach positive infinity. So if we look at it, the linear function and the cubic function both end in opposite directions. Pointing down to the left, up to the right, up to the right. So they end in opposite directions from their left side. Their left side is going to be pointing in one direction, decreasing. Their right side, in this case, is pointing in the other direction. Okay? And it could be flipped, but still those are going to be opposite directions. One's going to be increasing as we go towards its infinity, and the other one's going to be decreasing as it goes towards its infinity. The x squared and the x to the fourth, the quadratic and the quartic, notice how their ends, as they approach positive and negative infinity, are going in the same direction. On this one, they're both going up, okay? And on this one, they're both increasing as they approach positive or negative infinity. So I'm not talking about how they relate to each other, but how the ends within each function relates to themselves. So what is the relationship there between why are these have the same properties at their ends, and why do these have the same properties at their end? What is similar about these two functions and these two functions, but different between these two functions? Take a second, ponder on it, and I'll get some other stuff written up here on the board. So what did you come up with? What did you decide the relationship between these two polynomials are in their equations that makes their graphs have those similar end behaviors, and these two polynomials in their equations that makes their graphs have similar end behaviors? Hopefully you were able to come up with an idea similar to what I have here that talks about the degree being the same or similar, even and odd, that makes those graphs similar. And it comes back to positives and negatives. If I take a negative number and raise it to an odd degree, it stays negative. So a negative number to an odd degree stays negative. Well, a negative number to an even degree becomes positive. It's going to turn right back around and become positive again. Same thing here. It doesn't matter what that even degree is. So that's the distinguishing mark. That's what's going to tell us, are the ends going to point in the same direction or opposite directions? And that's if those degrees are even or odd. So that's the first thing we look at when we're trying to figure out end behaviors, is the degree, even or odd. From there I look at, are they going to be pointing up or down? Well, we know that every parent function starts as an increasing function. It decreases towards negative infinity, increases towards positive infinity like we have here. Now, every one's a positive increasing function as we go towards positive infinity. What changes the direction of a function? And that's the only way to change that is when we get that vertical reflection. We know vertical reflections come from a lead coefficient being negative. That number in front of your highest degree, if it's negative, that's going to cause you to have a vertical reflection. So that's the next thing we're going to look at. Leading coefficient being positive or negative is then going to tell us what's going on left or right. Now I should probably flip these around and look at what goes towards positive infinity first, because positive infinity, and this is how we say it, direction as x approaches positive infinity or negative infinity. And the reason I'm going to look at positive infinity first is because that's my normal stuff, right? The positive infinity is if I don't do anything as far as vertical reflection, finish positive, finish positive, finish positive, or finish increasing, 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 increasing. It's the left side that really is different in each of these. It's the right side is going to be the same, depending on your positive or negative lead coefficient. So let's look at what happens for positive infinity. If I have positive lead coefficient, we know that we're going to increase towards positive infinity. It doesn't matter what the degree is. If we have a positive lead coefficient, our graph is going to increase as we approach positive infinity. Negative lead coefficient, we've reflected our graph down, so our graph is going to decrease as we approach positive infinity. We're going down. Now the even and odd just tells me what the right side, the left-hand side is going to be, what we're doing as we go towards negative infinity. So what's going on? If they're even, they're going to be going in the same direction, either both towards positive infinity or both towards negative infinity. So even function tells me to go same direction with them. Odd function, not even and odd function. Even degree, odd degree. Even and odd functions are something different. That's coming up later on. Even degree and odd degree. Odd degree tells me that they should finish in opposite directions. And so if my positive infinity is an increase towards positive infinity, I'm going to decrease in the other direction. If I'm decreasing towards positive infinity, I've got to be increasing towards negative infinity. So that's the relationship. Positive lead coefficient for evens will be increase, increase. Positive or negative lead coefficient for evens will be decrease, decrease. Evens get the same. Positive lead coefficient for odds, I will increase to the right, decrease to the left. And negative lead coefficient for an odd, I will decrease to the right, increase back to the left. So this is what we're talking about when we're talking about end behaviors. What's my function doing as I approach positive infinity and negative infinity? As I move along the positive x-axis, is my graph going up or going down? As I move along the negative x-axis, is my graph going up or going down? That's going to give us a lot of good information about the overall shape of the graph. Now let's look at what's going on at our x-intercepts and how to actually find the y-intercepts so we can get a quick sketch of our polynomial. So let's start looking at the graphs and what happens at the x-axis around those x-intercepts. We know how to find x-intercepts, set your function equal to 0, and solve. So I've got a couple of them up here, two different things that are going on that I want to talk about. We know x-intercepts where we cross the x-axis. That's pretty straightforward from a graphing standpoint. Set each factor equal to 0, solve. Pretty straightforward through all that. Gives us our x-intercept of -2. Now something very special is happening at this x-intercept of -2. And notice how this quadratic didn't have two x-intercepts, it only had one x-intercept. There were two solutions to the quadratic. Okay, we got -2 twice because technically we have this plus or minus on the 0. So -2 plus 0 gives us -2. -2 minus 0 gives us -2. So what we would say is since that same x-intercept or 0, that's another word we call these, zeros. Might have an E in there, I can't ever remember. But anyways, these zeros, when they occur a multiple of times, we will write multiplicity of 2 because it happened 2 times. And this exponent's what's telling us how many times that's happening. There were 2 times that factor occurred, so 2 times we got that x-intercept or 0 of -2. So if we look at it, we have the x-intercept of -2. We know by transformations, my vertical and horizontal stretch are 1, so it's still up 1 over 1, and then that's our curve. For this cubic right here, x plus 3 cubed, same idea happens. I get this -3, but it was x plus 3, x plus 3, x plus 3, as we looked at with the x plus 3 cubed earlier. So that x equals -3 actually occurred 3 times. So I have x plus 3 3 times, and all of them, we'll pretend these are 3's, all of them were equal to 0. So 1, 2, 3 of them all equaled 0. So this 3 as our 0 occurred a multiplicity of 3 times. So that exponent, I probably should have picked a little bit better number. So it's not the x-intercept that tells us what the multiplicity number is, it's that exponent. How many times did that actually occur? How many times did that factor show up? Well, if we look at what's happening at this multiplicity, we know by transformations, my x-intercept was -3, we plotted that, and a cubic is odd, so I'm up on one side, down on the other, and it's a vertical and horizontal stretch of 1. So it's up 1 over 1, down 1, back 1. So transformations tell me that that's what my curve looks like. But the real thing we need to pay attention is, why is this x-intercept a pass-through x-intercept and this x-intercept a bounce-off x-intercept? We didn't pass through the x-axis right here. We touched the x-axis and turned back around. This x-intercept we passed through. So what is it that can tell me when I'm going to turn around at an x-intercept and when am I going to pass through an x-intercept? That's really, really important right there. And the thing that tells us that is that multiplicity. If the multiplicity is even, I'm a marker. If the multiplicity is even, we touch at that x-intercept. Or 0, whatever you want to call it. If the multiplicity is odd, we pass through. The x-intercept. Okay. Even multiplicity, we're going to bounce off that point. Odd multiplicity, we're going to pass through that point. So if it has if it only occurred one time, that's an odd multiplicity, we would pass through that. And it doesn't matter if it occurs 2 times, 6 times, 50 times. If that one specific 0 had a degree that's even, the 0, not the whole function, just that 0 has a degree that's even, then we're going to bounce off at that point. So we know how to describe end behaviors. We know how to be able to find x-intercepts, set each factor equal to 0 and solve. And describe their multiplicities so we can describe what's happening at the x-axis at each of those values. Last thing we need to know is how do I get that lead coefficient? If I'm going to be written in factored form, because that's what you're going to be presented with right now, because we're not to the factoring these things out yet. If I'm presented in factored form, how do I know what my lead coefficient is to know if it's positive or negative? And then how do I know what my y-intercept is? Because we know y-intercept is always the constant. It's the b in mx plus b. It's the c in ax squared plus bx plus c. It's when you have no variables left, no x's, what's going on at that y-axis. So if I want to be able to plot my y-intercept, and I need to be able to look at my lead coefficient to tell if it's positive or negative to get my end behaviors, how can I take something from this factored form I don't know, let's say we had negative 4x plus 2, that would be plus 1, x minus 3 squared, x plus 2. Say we had that right there and we needed to know the y-intercept, so we need to know what the constant is, and we need to know the lead coefficient so we can figure out our end behaviors. How can I get that from this information? Y'all take a second, pause the video, work on that, and I'll get all this other stuff cleaned up and a few examples for us to be able to graph. Alright, so let's see what y'all kind of came up with. What was the technique to be able to figure out what my lead coefficient is and what my constant is? Because that's going to give me my end behaviors and that's going to give me my y-intercept. Well, we know that we could just multiply all this stuff out, so let's look at multiplying. First, I'm going to put these two together, this negative 4x plus 1 and x plus 2, and I'm going to do the x minus 3, write it out, and we'll put the first two together and the last two together. Negative 4x squared minus 8x plus x plus 2. So I get negative 4x squared minus 7x plus 2. On this one over here, x squared minus 3x minus 3x plus 9. So x squared minus 6x plus 9. And then we put those two together. Negative 4x to the fourth plus 24x cubed minus 36x squared minus 14x squared plus 42, minus 14x cubed plus 42x squared minus 63x, put our 2 on there, 2x squared minus 12x plus 18. Okay. Now, assuming all my arithmetic is correct there, I get negative 4x to the 4th. I get plus 10x cubed. I get 4436 is 8, hopefully. 8x squared minus 18x plus 18. But none of that really matters because I'm looking for two things. I'm looking for the constant, right? And I'm looking for that lead coefficient. First term and last term. So let's look at, I could do this every time to figure out my lead coefficient and to get my constant right there so I can get my y-intercept. But I don't want to have to do that. I should be able to look at this and tell what's my lead coefficient and what's my constant. All of this is irrelevant because I should be able to look at this and get those two pieces of information right there. I should be able to know negative 4 is my lead coefficient and my degree is x to the 4th because we also need to know that, and 18 is my constant because that's really all I need. If I know my first term and my last term, I've got my end behaviors and my y-intercept, and if I solve each of those, I have my x-intercepts. So how can I turn this into just first term and last term? Well, it comes from putting together first terms negative 4x x squared, because this one happened twice, and x, and my last terms. One, negative 3 squared, and 2. So when I put that together, negative 4 times 1 is negative 4. X squared and x is x to the 4th. And then here, negative 3 squared is 9. 9 times 2 times 1 is positive 18. So, without going through and doing all the multiplication of the entire polynomial, if I put my first terms together, that should give me my overall first term, which tells me degree and degree and lead coefficient for end behaviors. And if I put all my end terms, my constants together, the constant is made up as a product of the constants. And this is a it may seem trivial right now. It's a very, very important concept that we get to because it's how we're going to be able to go from this long expression we had down here to get back into this, because that's going to be our end goal as we work our way through this unit. Taking a large polynomial and turning it back into those factors so we can get the x-intercepts. Okay, so very important concept that we have, that the first term, the lead coefficient, and the degree comes from a product of all of the first terms of our linear factors. And the constant comes from a product of the constants of all of our, is a product of the constants of all of our linear factors. May seem trivial, but it's very, very important that you understand where those numbers come from as it relates back to the linear factorization. All the factors of x to the first degree that give us this polynomial that we had down here. So that's what we're going to be looking at. So let's take this example that I've got right here and let's sketch a graph. So to get end behaviors, I need two things, degree and lead coefficient. So we know, as we just saw, we're going to do that by putting together our first terms, 2x, x squared, and x to the first. The exponent has to be a part of it. So when we do that, we get negative 2 x to the 4th. Now, end behaviors will tell me that my lead coefficient is negative and my degree is even. So, degree even lead negative. So I know that my end behaviors towards, there's my negative infinity, there's my positive infinity. Even tells me they're going to be the same. Negative tells me that I have to be decreasing on the right side. Okay? And the even tells me that I've got to be decreasing on the same side. So, if you'll remember, if you'll look back at the table, if you're not, if you haven't got it in your mind yet, lead coefficient is negative, tells me I'm decreasing over here. Degree being even tells me I've got to do the same thing on the left side. So the lead tells me the right side, the even or odd tells me to do same or opposite on the left side. So this is what my graph should end up. It should end up pointing down. Well, let's let these other numbers should confirm that. So let's look and see what happens with them. X-intercepts come from taking each factor, setting them equal to 0 and solve. So if I take my negative 2x plus 1 equals 0, subtract 1, divide by 2, x is equal to a half. Shouldn't have to show you all the mechanics of that. X plus 2 quantity squared. So x plus 2 is the 0. Set it equal to 0. Solve. X is equal to negative 2. That quantity squared tells us it's a multiplicity of 2. So x plus 2 squared, that right there tells us multiplicity of 2. And then the x minus 3 equals 0, x equals 3. So these are our 4 intercepts, our 4 zeros. And it's something that's very important, that a fourth degree polynomial has 4 zeros, whether they're real or imaginary, and that's something we're going to get into a little later on, is the degree of the polynomial has to match the number of complex zeros it has. Whether they're real zeros or imaginary zeros, the total number of zeros has got to equal the degree of the polynomial. Very important thing. Go ahead and get that in your mind and get that mind wrapped around that right now because we come back to that again and again and again. And then the y-intercept. Y-intercept we know is from taking our constants. It's a product of all the constants. So 1 times 2 squared times negative 3. So 2 times 2 squared is 4 times negative 3 is negative 12. So that gives us everything we need. I know where my y-intercept is. I know where my x-intercepts are, what's happening at the x-intercepts, whether we're passing through or bouncing off. And I know where the ends of my graph are. So let's get a picture. So we should end like that. X-intercepts are at a half, negative 2, and at 3. Okay, so there are my intercepts, and my y-intercept is at negative 12. And we'll just say somewhere down here. I don't have to draw all the way to negative 12, we're just getting kind of some important numbers. So, well, the way you start drawing it is just go from the left side to your first x-intercept. Now at negative 2, we had an even multiplicity. So even multiplicity tells me to bounce. So I'm going to bounce off that 2. The next point I get to is that y-intercept. Now, whether we're changing direction on the left or right, we don't know. And frankly, we don't care. Right now, I can change direction at that. These points where we change direction, they're called, you'll actually learn how to calculate them as you get into calculus. Those are critical points where you turn direction as your inflections. But you'll get into those. Those are critical points. Those local maximum, local minimum, how far down you're going. So we're not getting the exact picture. We're just getting kind of a general idea of some of the key features of it. But you get the idea. Just turn it around somewhere, and it passes through negative 12. Then we come back up to 1/2. 1/2 occurred one time, so it's a pass-through. And then come back down to the 3. Again, it's a pass-through because it occurred just one time. And then that's our picture. That's our general shape of our polynomial. And it kind of matches up because we said 4th degree polynomial, right? Degree was 4. 4th degree polynomial should have at most 3 turnarounds, 3 changes in direction. And it's not, again, not 100% accurate. I don't know how far up this point was. I don't know where the turnaround was, whether it was down here or whether we came through and then came back up. Those we don't know right now because we don't have those calculus techniques yet to be able to get that. But we know the general shape, we know some key features, we know what's going on at the x-axis and ends. Those are very, very important things to know. So, this is the technique for getting a sketch of a graph of a polynomial. Give me a second, I'll get a couple of examples up here for you guys to try. So here we have a few examples that I want you guys to take a crack at. Pause the video, remember to find these 3 features, and give me a quick sketch of each of these 2 polynomials, and I will wait right here, guys. Hopefully you were able to get a couple of really nice graphs. Let's check your work, see how you did. So in behaviors, first thing I do is I'm going to put all my lead coefficients together to get the overall lead coefficient. So negative 1x to the 3rd power, negative 2x to the 4th power. So when I go through and do that math, negative 1 to the 3rd is negative 1. Negative 2 to the 4th is 16. So negative 1 times 16 is negative 16. X to the 3rd, x to the 4th is x to the 7th. So from that I can see that I have odd degree negative lead coefficient. So we can build our graph, or start building our graph right now off of that. So negative tells me I'm going to be decreasing on the right as I go towards positive infinity. Odd tells me I'm going to do the opposite on the left. So I should be going towards positive infinity on the left side, or increasing as I go towards negative infinity. So negative is decreasing on the right, odd means opposite. Now we need to find out what our x and y-intercepts are. So take each factor, set it equal to 0. So x equals 1, just add the 1 over. But this exponent tells me that that 1, I can write it like a MULT dot. That's short for multiplicity right there. I can write, this exponent is what tells me that the 1 occurred 3 times. So multiplicity of 3 for that 1. Which tells me that that's a pass-through point. That's all we really need the multiplicity for at this point. Alright, then we're going to take the negative 2x minus 5 equals 0. Add your 2x over, divide by 5, so x equals negative, add your 2x over, divide by 2, get negative 5 halves. And that has a multiplicity of 4. That's even. 4 is an even number, so that tells me it's a bounce off point. Touch but don't pass through. And then our y-intercept. Y-intercept comes from the constants, our last terms. So 1 to the 3rd and negative 5 to the 4th. Well, that's 1. That is 625. So 625 is our y-intercept. Let's start plotting all of these points. So the y-intercept is obviously going to be somewhere up here. Doesn't have to be drawn to scale. X-intercepts are at 1 and negative 5 halves, negative 2 1/2. So 1 or negative 5 halves and 1. Now we just connect the dots. You can go from left to right, right to left, it doesn't matter. I'll go from left to right. So we're going, as we approach negative 5 halves, it was even, so that told us to bounce off that point. So I'm going to come into negative 5 halves, bounce off of it. Should probably make it actually touch it. Keep going on up. And it can do a lot of weird stuff. I mean, this is x to the 7th power. There could be all kinds of stuff going on in here. So we don't know for sure, but we do know eventually it's going to get to 625, and then somewhere it's going to turn around. I don't know if it went up here and then turned around, or if it goes and actually turns around at 625. Remember, you have calculus techniques you'll learn to teach you how to do that. But we just know that somewhere it's going to turn around. And then pass through the positive 1. So then we'll pass through positive 1, and we just keep on decreasing as we move along. As we move along the x towards positive infinity, our function decreases. So that's the curve right there. Now remember, your degree is maximum number of terms. Okay, I don't have to have 6 terms in there. I just have at most 6 terms in there. This one could have 3, and it could have more. Remember, I could have all kinds of little wiggles in here to pick up all those extra terms that we're not seeing because, like I said, we lack those calculus techniques. All right, let's see how you did on the other one. So let's go through again. End behaviors. End behaviors come from taking our first term in each expression here. So this one's a little bit tricky to see, but you can just take this whole monomial. That is your first term in this first expression. So, and we'll look at it in a little different manner in a second when we get ready to do the y-intercepts. But for right now, it's a variable term, so we can just take the negative 3x to the 10th, negative x, and then positive 3x. So we go through, we do arithmetic, negative 3, negative 1, positive 3 is 9, x to the 10th, xx is x to the 12th. So we have even degree with a positive lead coefficient. And make sure you're paying attention to what you're doing there. Even describes the degree, positive describes the lead coefficient. So positive tells us we're going to be increasing on the right side. Even tells us we do the same on the left side. So that's what our ends should look like. X-intercepts. Let's take each factor, set it equal to 0 and solve. So negative 3x to the 10th equals 0. Negative x plus 2 equals 0. 3x plus 4 equals 0. So divide by 3, take the 10th root. So you're going to get 0 with a multiplicity of 10. Which, since that's even, that's going to tell us it's a bounce point. Here, for the second one, add your x over, so x equals 2. Okay. X equals 2 is 1 time, so that's a pass-through point. And then 3x plus 4, x is equal to, subtract the 4, divide by 3, negative 4/3. That's also going to be a pass-through point. Because that's 1, 0. That negative 4/3 only occurs 1 time. And let's finish up with y-intercept. Y-intercept, I'm going to take my constants. Now this is where it gets a little bit tricky. I need to realistically be thinking this as negative 3 times x plus 0 to the 10th power. We write all these as a product of linear factors. This is the linear factor. It's raised to the 10th power. It's not the negative 3x. It's not negative 3x to the 10th power, because the 10 is only on the exponent. So only the exponent is x plus 0 to the 10th power. So this is realistically what's going on right here. So if I take my constants, I've taken 0 to the 10th, 2 to the 1st, 4 to the 1st. So all that's times 0 is going to equal 0. So our y-intercept is going to be 0. Our x-intercept is 0. Our x-intercept is 2. And negative 4/3. So somewhere around about there. So that's what our graph for our intercepts, our key points look like. And now we just connect it, going from left to right. I'm coming into negative 4/3. I'm going to pass through negative 4/3. I'm going to turn around somewhere before I get to the y-axis. Okay? Got to turn around somewhere before the y-axis, get to 0, and then I'm going to bounce off of 0. So I bounce off at 0, and then I've got to go back and I've got to pass through 2, so I'm going to have to turn around some other point and finish out my graph. So the function will look similar to that. Now you can go into y equals on your calculator, go to y equals, type this in, check the graph, and you'll see something very, very similar to this figure. So you can always use that as a check to make sure you set it up. I just want y'all to be able to look at a polynomial and kind of get an idea of what the function is doing overall, without having to do all the calculations of where's this point, this point, this point, that inflection point, that inflection point, that inflection point, all that stuff. Without having to do that, we can still get a general idea of what the overall shape of it is. I know I've thrown a lot of stuff at you in this lecture, a lot of terminology, but that is our introduction to polynomials. We know how to classify them, we know how to multiply, add, and subtract them, and we know how to get their end behaviors, x-intercepts, y-intercepts, and sketch a quick graph of them. A lot of stuff, a lot of terminologies, kind of get a lot of that terminology in your mind, start talking math instead of just doing math. And I will see you in class tomorrow, guys.